Okay, so here we have the next question on the menu today. It is asking us, or is presented the following situation. Okay, we are exploring a cave, a spelunker. I guess that's like not. It's a cave explorer. A spelunker starts at the entrance and moves the following distances. Okay, so um, let's actually like kind of draw this out as we read through this, because at the end we're going to try to find the resultant displacement, how many meters of displacement, and in what direction. Okay, so let's say this is our starting point right here, and the first step is we're going to go 75 meters north. Okay, so I'm going to try to be on the grid and be fairly consistent with my distances. Okay, so 75 meters north is our first step, and then 275 meters towards the east. Okay, this is going to be very difficult to draw to scale now. 275 meters east. Not 27, 275. Okay, I'm actually going to need to move this whole thing because I didn't realize how much east we were going. Maybe down to here. Okay, cool. Back to action. The next step is 175 meters at an angle 30 degrees north of east. So we're going to go directly east, but just slightly north of that by 30 degrees. Let's get our pen here. So something like this. Okay, comes 30 degrees north of east, and that was 125 meters. 175 meters, my bad. And our last little step of the journey, 150 meters directly south. It's going down for real. Something like this. Okay, so our first thing that we're going to try to find here in this situation, to draw this more precisely, is like this. We are looking for this little angle, or this vector right here. This is our target. We are looking for its magnitude and as well as its angle. Now, from the way that I drew this, it looks like target is going to be like south, like southeast, but that could just be my drawing errors, right? So keep in mind that these are not necessarily to scale. It could also be pointing this way as well, depending on you know how to scale your drawing is. But this is like the general gist of it. Essentially what we're trying to do is we have a vector situation right here, right? So we see that the red target arrow is the same as this like head to tail chain of all the steps that were described in the question. Essentially what we're going to try to do is treat all of these individual steps in the journey as individual vectors, add them together, and then that's going to be the target. Okay, so how we're going to do that, let's call this A, let's call this B, let's call this one C, and let's call this one D. Okay, fairly straightforward, and they're all vector values. So if we wanted to maybe let's just call this T for target, we know that the value T as a vector, that's going to be the vector sum of A plus B plus C plus D, like this. Plus C plus D. Okay, so conveniently, a lot of these vectors are in one, are like perfectly in the north-south or east-west direction. But C, this C vector is, you know, it's northeast, so it's going to be a little bit more difficult to deal with. That means what we're going to need to do here is we need to convert all vectors into Cartesian form. Essentially what Cartesian form is like I and j with the unit vectors. These will be our unit vectors. And I is going to correspond to east being positive for I, and j is going to correspond to north being positive. Okay, so instead of using like north, east, south, and west, maybe you might be more familiar with a Cartesian system like this of x and y. You know, we still have two perpendicular directions, but it's just like a different way of representing them. Yeah, so just imagine like east and north as our stuff like this, and how we're going to make these vectors with I and j components in Cartesian form is actually fairly straightforward. Okay, so let's take a look at our first step, which is A. A is just 75 meters to the north. It does not have any east-west movement, so it's purely going to be a j vector. It's only going to have one term in it. Okay, so how much it's going north, so it's going to be a positive j term, and 75 meters is how much it is. So to write this out, A as a vector is equal to positive, because we're going north, 75 in the j direction meters. Okay, now what about B? B is kind of similar. We're only going east-west, no north to south movement. So there's no j term associated with the B vector. It's just going to be I. So if we wanted to write out our B vector, we are going to be going straight towards the east, and east is our positive I direction. So this will be a positive term. Our magnitude, 275 meters in the I direction, and meters. Okay, fairly straightforward. Now C is going to be a little bit spicier, because you can see C has both some horizontal movement, like it's moving horizontally by this much, and it's moving vertically by this much. Okay, so we need to pretty much, what's going on here in green is we're going to like redraw C as like CX component and CY component. Okay, because so essentially what this means is that C as a vector is going to be CX component in the I direction plus CY component in the J direction. Okay, so how do we find CX and CY? They are really just going to be these lengths right here, and if you look closely, this looks like a right angle triangle. With the right angle being here. What do we know about right angle triangles if we know the hypotenuse? That's the 175, that's our hypotenuse, and the angle here, does that ring any bells? So Kotoya told me? So Kotoa, does that sound familiar? It sounds familiar to me. So that's essentially exactly what we're going to be doing here is our CX component is just going to be you know, it's adjacent to the angle, so that's going to be cos 30, 175 times 175 meters. And CY, well, that's going to be similar, but on the other side, it's going to be sine, hypotenuse and opposite, SOA of the SOA Katoa. So sine 30 degrees, 175 meters. Okay, so these are the individual x and y components of C, just using the power of trigonometry. Okay, so let's write out C as a complete vector here. Okay, so we know that the x component is going to be cos 30 times 175. Let's actually get that as a calculation ASAP fast. My cosine is not that quickly done in my mind, so I'm going to use the calculator for that. And I got 151.55, and this is in the east direction, so it's going to be positive. So positive 151.55 in the I direction, and in the J direction it's also going to be positive, and it's going to be sine 30 times 175. So 175 times 130, that is 87.5. That is positive. Plus 87.5 in the j. And with these multi-term vectors like this, you can surround them by brackets and put the unit outside. It means the same thing, and you don't need to write like meters on every single term. It's not really a big deal when you're in 2 dimensions, but these vector concepts will still be the same if you go to like 3 dimensions or even 4 dimensions if you go into like theoretical physics with like the curvature of space-time and all that. You don't need to worry about that right now, but it's just a good thing to keep in mind. Okay, and our last vector is d, our wildly not to scale d right here, but it's going straight down, so that's fairly easy. Going straight down, that's purely in the j direction, and because north is positive and is going straight down, it's got to be negative j direction. Okay, so it's going to be negative 150j for d. If you forget that negative, big trouble. Negative 150 j meters. Okay, now we just got to put them back into here, and we can get our t value. Okay, so A is plus 75j, and I'll write meters all at the end. So this corresponds to A plus our B vector, which is 275I. Okay, that's our B. Plus our C vector, which is 151.55I plus 87.5J. That's our C. And our D is going to be negative 150 in the J direction. Okay, so essentially to do this math, if you're not already familiar with it, we're going to try to combine all of our terms that are I and all of our terms that are J. Okay, so underlined in red are our I terms, and underlined in green, those are the J terms. Okay, so the result of T, the I component is going to be the red terms together. So that's going to be 275 plus 151.55. Okay, so overall, we've gone 426. 426.55I. And then for our J, we got to put all the green terms together. So we got 75, that's a positive, plus 87.5, also a positive. But, oh, don't forget that negative, minus 150. Okay, so that is, as a result, positive 12.5 J. Looks reasonable to me, and that is all in meters. Okay, now does this make sense? It means that we went 426 meters towards the east, very far east, and barely any, and just like 12 meters north. So my diagram is a little bit wrong. I think that's because D I drew a little bit too long, so we would actually expect our target to be pointing upwards. So we would actually expect it to look something like this. That's what it would look like. Okay, so it's asking us how many meters this is. So essentially what this means is we need to find the magnitude of this vector. Because what's really being represented here is we know that this is going to be 426.55I, and we know that this right here, that's going to be 12.5J. Okay, now if you look closely, another one of those right angle triangle situations, and we know the two side lengths, and we're trying to find the hypotenuse. Do we know how to deal with this? Yes. The power of Pythagoras theorem. Okay, so to write T as a magnitude, it's typically written with a absolute value like this. Sometimes you'll even see double absolute value, and that's just to like be double sure that this does not get confused. It's just to say the magnitude, and you calculate this with a Pythagoras theorem type of operation. Okay, so we have our I term, 426.55, and we're going to square that and add it to 12.5 squared, all under the root. Okay, we don't really need to worry about plus minus on this one. So we just got to take this calculation too fast, ASAP fast. Okay, 426.55, square that, add 12.5, square that. Take the result of that and put it in the square root, and my result is 426.73 meters. And that is a reasonable answer, and that's because because the horizontal, the east, is so much larger than the north-south direction, we would expect that our t is going to be very, very close to our I, just because I is so much larger than j. So that makes reasonable sense. Okay, so this is our total meters away. That would be yeah, we got the same calculation here. That's awesome. Okay, now to find the angle, essentially we're looking for this little angle right there. That's that theta angle. And another one of these right angle triangle situations we could think back to SOHCAHTOA. We know that our tan is related to the angle as well as the opposite and adjacent. We know tan theta is equal to op over adjacent. So if we were to isolate theta, we just got to do tan inverse of the opposite divided by adjacent. So the opposite in this case, 12.5. That's the j component, the vertical or north-south component. Okay, so 12.5 and divided by adjacent 426.55. Send that through the inverse tan, also known as arctan. And let's see what that is. So 12.5 divide 426.55. The result of this calculation I got is theta is equal to 1.68 degrees, and is going to be this way. Okay, so just counterclockwise of a horizontal towards the right angle. Okay, and it's good to like draw a little symbol like this what I got right here, to kind of specify which direction or where this angle is respect to. Okay, so yeah, that would address all parts of this question. And how much are we north of east? That's essentially what this diagram is saying, or this little image is saying, 1.68 degrees. Okay, very small angle, but still noticeable. Just a little rounding discrepancy there, but otherwise this is a perfectly reasonable solution. That's awesome. Okay, big high five. Here above, solution is good. Good job, high five. Ain't that fun?